The area of a parking lot is 600 square meters. A car requires 6 square meters while a bus requires 30 square meters. The attendant can only handle 60 vehicles. If a car is charged $2.50 and a bus is charged $7.50, how many of each vehicle should be accepted in order to maximize profits? First, we want to define our variables. We should let C represent the number of cars, and B can represent the number of buses. Then we want to look at some things that we are limited by. We will write those as constraint inequalities. Here are some constraints. The parking lot is only 600 square meters, and the attendant can only handle 60 vehicles. If it can only handle 60 vehicles, the number of cars plus the number of buses must be less than or equal to 60. For the other constraints, it says that a car requires 6 square meters and a bus requires 30 square meters. So we have 6C plus 30B, and that must be less than or equal to 600 square meters. The implied constraints are that we have to have a positive number of cars and buses, so both C and B must be greater than 0. Next, we're going to write our objective function. The objective, or the goal, is to maximize profits. So we're going to look at information that has to do with the amount of money. Cars are charged $2.50 and a bus is charged $7.50. So the objective function, P for profit, is 250C plus 750B. Next step, we will graph our constraint inequalities. It doesn't need to be a perfect graph, we are just making a sketch, and so I just like to do the L shape to represent our axes. Keeping it alphabetical, X comes before Y, so let's put B on the X-axis and C on the Y-axis. Looking at the first constraint, the C-intercept is 60, and the B-intercept is also 60. So 60 to 60. Go ahead and connect those. And if we do our test point of 0, 0, 0 is less than 60, so we will shade toward the test point. To graph our other constraint, if we cover up the C and solve for B, we can get the B-intercept. 600 divided by 30 is 20. On the B-axis, we're going to label it 20. And if we cover up the B and solve for C, 600 divided by 6 is 100, so that will be the C-intercept. If we do our test point of 0, 0, 0 is less than 600, so we will shade toward the test point. Our last two inequalities, C greater than 0 and B greater than 0, will look like this for the shading, and we see the section of overlap. We want to highlight the 4 corners, the 4 vertex points of the shaded region. We are going to make a list of these vertex coordinates, keeping them in the order B, C. So we have the vertex 0, 0, 20, 0, and 0, 60. To get the last vertex, we need to solve the system of equations created by the 2 inequality lines. Notice how when we turn it into the system, we replace the inequality symbols with equal signs, but these equations come directly from the constraints. If we multiply everything in the top equation by -6, that will allow us to solve this system using substitution. I'm sorry, using elimination. 6c plus -6c eliminates, so we're left with 24b equals 240. So b is 10. And plugging that back into the first equation, c plus b equals 60, that means that c must be 50. So we will add this point to our list of vertex 10, 50. For the profit, because this is b before c, we're going to rewrite those profit equations so that b comes before c. That will make sure that you're plugging your numbers into the right places. Now we're going to test each of the combinations from our vertex points to get our profits. So it looks like the combination that's going to give us our maximum profit is the last one where we have 10 buses, 50 cars, and that's going to give us a maximum profit of $200. So to state our final answer, we're going to give some meaning to these numbers. 10 buses, 50 cars, max profit is $200.